Cozzi. I'm from Cesium, now part of Bentley Systems. Before we jump in, I want to get to know each other a little bit. I'm curious, how many folks are currently working on Gaussian Splats, whether you're researching, prototyping, or have a product? Wow, okay, so maybe at least half the people. Okay, then for folks who aren't actively working on it, how many folks beyond this session are just currently researching use cases, kind of trade-offs, and so on? Okay, so we're all interested in Gaussian Splats. Very, very nice. So folks, I'm also the co-chair for the 3D Asset Interop group at the Metaverse Standards Forum. So I'm going to do a quick overview of the forum and how we've been trying to support Gaussian Splats. Then we have a series of 7-minute lightning talks from many folks, and I'll help moderate. And then we're going to have a Q&A where everyone can participate and share your use cases and your perspectives. All right. Another reminder is we'd love, of course, take notes, but the video from this and the slides will be available on the Metaverse Standards website afterwards. And photography, not photogrammetry, is welcome during this session. And please post on social media and tell the world what you think about Gaussian Splats.
Photogrammetry is not.
All right, folks, so the Metaverse Standards Forum is a nonprofit that's bringing together companies, universities, and SDOs, standards defining organizations, to help with both pre-standardization efforts and post-standardization efforts. So for example, for pre-standardization, we might help gather use cases and requirements, like we're doing right now for Gaussian Splats. And then for post-standardization, we might help fill in gaps with sample models, test cases, that sort of thing. We started about 3 years ago, right when the metaverse term was at peak buzz, and there were 2,600 organizations of all different sizes involved. As we think about Gaussian Splats, there's been so much research and so much development in the last couple of years. We really want to ask ourselves, okay, when in that life cycle do you want to consider a conversation around standardization? Right, if we wait too long, is the mic not working?
Oh no, we just can't hear you through the mic very well.
Okay, I'll try this mic. How's that? Better?
A little better,
Right,
yeah.
cool, sorry about that. So when you think about standardization, we don't want to wait too long because we could end up fragmenting the ecosystem of all of these products using different types of formats and different representations. But at the same time, we don't want to standardize too soon or standardize in the wrong way to prohibit any research until it's been actively developed. So the way we've been trying to support this over this past year, since January, we've been hosting a number of virtual town halls to talk about Gaussian Splats. The first one we did in January, and we announced it on like 3 weeks' notice. We had over 400 people come and over 15 organizations present, sharing everything from what they're doing on the web, what they're doing with their twins, what they're doing with avatars. So then we followed that up with a second one where we went deeper on end-to-end pipelines from the data acquisition, the processing of the splats, to ultimately rendering. And then most recently we did one with the research community to get the research perspective on standardization. And we thought, well, geez, there's no better place to continue this conversation than here at SIGGRAPH, right? It's bringing together both practitioners and researchers as well as engineers and artists. So here we are. This is the series of our presenters today. Again, we're going 7 minutes each, and then we're going to do a Q&A with all presenters at the end of the session. So I encourage everyone to stay for the whole session, queue up your questions, and we're looking forward to engaging. So with that said, there's no better person than Michael from Radiance Fields to give us an overview of Gaussian Splats. Michael, come on up.
Okay, thank you so much for everyone for coming out today to talk about Gaussian Splatting. So my name is Michael Rubloff. I started a website called radiancefields.com about 3 years ago to start to really go through and catalog the progression of this really exciting technology. And so for today, I'm going to be going through about a quick overview about where the technology is, where it's being deployed, and what it might look like in the future. So just to go through really quick about the foundations of Gaussian Splatting. It was published in late April of 2023 with co-first authors Bernard Kerbel and Yorgos Kampanis from INRA and GraphDeco. It won Best Paper at SIGGRAPH 2023, so just 2 years ago, and one of the things that Gaussian splatting can do for people who are not familiar is that it's able to reconstruct these things which are known as view-dependent effects. So in the real world, we expect light to reflect and move in a certain way, and Gaussian splatting is able to handle this. In the 2 years that have elapsed since its initial publication, there have been significant advancements in the actual technology, and that goes to reconstruction time, the fidelity of it, the compression, the input sources that are able to be used for Gaussian splatting, and the tooling as well has really begun to be evolved. And again, it's quite interesting. So 3D Gaussian splatting, the full name of it, as you can see on this here, is 3D Gaussian splatting for real-time radiance field rendering. So it is a way to render a radiance field in real time. But as we have seen, this is a very, very quickly evolving space. And the two most popular radiance field methods are Gaussian splatting and NeRF's neural radiance field, but they're not the only ones. And so here's just a quick collection of some of the other methods that exist out in the world. And there is tremendous research interest, and the best practices I don't think had to be said that they've been fully discovered yet. But I think what can be fully said is that Gaussian splatting is definitively the first bridge to industry adoption of radiance field-based representations, and it is being shipped today. So some advantages as to the state of Gaussian splatting. Let's say there was a video here. See, there it goes, from Esri, where we can actually start to see what the advantages of Gaussian splatting is. And some of these include, it is able to render in much faster than real-time rates. They can be reconstructed from pure 2D images. So this is all that you require. You don't need any specific proprietary camera type. You're able to really just feed it 2D. And as we start to see as well, they can scale quite large. In fact, they've actually proven that they can scale infinitely, given enough compute and input images. And the train times are actually radically plummeting too. There's actually a paper here at SIGGRAPH this year, which is now reconstructing Gaussian splatting, depending on how many images you feed it. I think it's like 32 images in about half a second right now. So as we take a look as well as the progression of imaging, so in our lives we've mainly interacted with imaging in a 2D capacity through photography. And as we can see here as well, this is kind of no longer the case, because now through Gaussian splatting and other radiance field representations, it allows us to reconstruct not just a single viewpoint, but really an explorable and interactive 3D environment. And so it lets us do novel view synthesis and fly around the world. As it also stands, we are also able to do dynamic reconstruction. So this looks like a normal, 2D video of Henry Pierce from Infinite Realities just making some expressive faces. But these are full dynamic 3D reconstructions, and we get a sense as to the potential fidelity as well that we can pull. And we'll see some more really exciting examples from some of the speakers today about that. And it's also not really known, but this technology has also already been shipped in very large major motion pictures that have been released to the public already. And they look so lifelike that people do not realize that they're actually looking at Gaussian splatting. The last thing that I want to touch on as well is the world of generative Gaussian splatting as well. So I have this example from World Labs, which we can kind of see as well, where we can actually generate these captures to be from either a single input image or text as well, but they'll have some examples as well. So just to give a quick overview too about where it is in the actual industry software pipeline, it's actually being adopted quite rapidly from the existing industry software. So here's just the list of some of the places that you can find support for it already. Okay, and the last thing that I want to just touch on as well is that we are seeing it being shipped in some of the world's largest industries and world's largest companies, as we'll hear from today. So we're seeing it in hospitality, live events, cultural heritage, e-commerce, journalism, healthcare, federal and defense, insurance, automotive, robotics, and significantly more. And so basically, if you are an industry that is investigating or using 2D right now, there is going to be a very large use case for lifelike 3D. And so I'm excited to really pass forward the conversation to some of the companies that are shipping it and using it out in the real world right now. But I think it is really important as well to talk about standardization too, because there are so many industries that are all adopting and trying to actually leverage this lifelike 3D capability. It's going to be very important that we have some level of standardization, but given the pace of research and where the technology is as a whole, this standardization should definitely be both modular and extensible in nature. But that said, there are some really amazing talks and examples following me immediately, so I'm gonna pass it forward to Jason and Tam to show how the geospatial world has been using Gaussian splatting.
All right, thanks again, Michael. Really good intro, and it's great to see all of the industry adoption as well as research moving things forward so quickly. So next up, we are going to hear about geospatial and using GeoTF. We have Jason from Cesium, who's over the last couple of years has been dedicated to rendering Gaussian splats. And then Tam from Esri, a geospatial expert. Tam and I met 10 years ago here at SIGGRAPH. That's right. So over to you guys.
Thank you. Thank you, Patrick, and again, warm round of applause for Patrick for leading this.
So, Jason and I want to talk to you about a little bit about how and what we're doing to enable geospatial 3D Gaussian splats, and particularly GLTF. Now, over the past year, you've already seen tremendous advances in 3D Gaussian splatting, as a technique for delivering photorealistic 3D scenes with incredible detail. But really, to make it useful and usable in geospatial workflows, it needs to be interoperable, it needs to be efficient, and it needs to be open. So then we looked around and said, what is there out there that actually can do that? And of course, there's GLTF. And GLTF is already widely adopted as a 3D transformation format. It's lightweight, it's open, and it's supported across industries, including from gaming to GIS. So we thought about integrating Gaussian splats into GLTF through new extensions. We're enabling the same portability and ecosystem benefits that we have enjoyed for many years through GLTF, for point clouds, for meshes, and the likes. So we really set up with a singular goal or mission, to bridge this cutting-edge rendering technique with practical needs of the geospatial community. We're trying to make splats streamable, editable, and standards compliant. So let's look at some of the challenges and opportunities really that we've been looking at to fulfill this geospatial visualization needs. So you might ask, what makes 3D Gaussian splats exciting for the geospatial industry, and what are the challenges that we're facing? Well, two aspects stand out. Streaming and display performance, and interoperability and standardization. But before really delving into that a little bit, I just wanted to bring up to your attention common workflows in geospatial, from data acquisition, whether it's satellites, drones, or terrestrial capture, and some form of processing, whether it's online, on-prem, on desktop, and then delivering it through your applications that you're all accustomed to using. Cesium.js, the ArcGIS platform, Niantic Spatial, you name it. Now, all these experiences actually lead upon to particular layer types and data types that geospatial workflows really tend to work in. Is it for change detection, image classification, object detection, or point cloud classification? Those are the layers, or the lingua franca, really, geospatial that we work in. So, really, our idea and intent here is to use open formats, open standards, GLTF, and even working with OpenUSD to actually create a format, a standard that actually is able to interrupt between different applications, different workflows, using GLTF and 3D tiles as a medium. So quickly, the issues and challenge that I mentioned, streaming and display performance, when we're talking about that, is conciseness. We're talking about, a higher order harmonics could actually reduce the data without losing quality. But how about file compression? How about the level of detail? In 3D tiles and I3S, we're all accustomed to having level of details that allow us to load vast amounts of data. Those things need to be considered and worked out here as well as GPU compression. But now, interoperability is also big, as I said, to be able to use this content in all different application mediums, you need to be able to have interoperable and standardized way of doing it. So challenge and display Gaussian splats actually also bring challenges as far as how you display
and the display algorithms that each application employs. Conciseness of the representation. New radiance fields, Michael just mentioned it right now. There are many that are out in the industry, and we don't want to be excluding any new thing that will come, but we also want to be practical in bringing geospatial experience to those splats. So with that, we really asked this question and said, should we build on open existing standards, or should we just start from scratch? And the answer was emphatic yes, we should build on open existing standards. So I'll pass it on to Jason to tell us how we're actually doing that. Jason.
Thank you, Dan. So at Cesium, we believe it's important to have open and standardized ways of storing and distributing Gaussian splat data. And this has been an open collaborative effort from the beginning, starting with Chronos and the 3D formats working group and the GLTF community at large, and then more recently Esri and Spatial as well. Having a better way to store this data is great, but we also want to facilitate reducing industry fragmentation and enhancing interoperability, which we see our GLTF extension being one path to achieve this. We've been impressed and encouraged by all the community feedback, as well as the coordination and cooperation of companies like Esri and Spatial. We're not only helping direct this effort, but building momentum and legitimacy to what we're trying to achieve. We're continuing to iterate and take feedback from the community and how we can bring this format to not only Geospatial, but the broader market where anywhere Gaussian splats might be a good user. All I said, I think it's, we believe in standardization because we're working on it right now. We have 2 proposed extensions in draft form today. We have the base extension, which we see serving as a foundation for future extensions within GLTF. And this is our primary focus for ratification currently. In addition, we also have a draft extension that incorporates the SDT compression from the Spatial. Beyond GLTF, OpenUSD also has work going on, and we've actually done some collaboration with them and brought some ideas from what they're doing into our base extension. And there is another MSF presentation later today with Patrick and some other colleagues that'll go in depth on that. So looking at it more closely, we can kind of see the structure of this baseline extension really serving as the foundation of not only the current work with SPC, but any other compression formats that may come out or serve the needs of other users. If SPC isn't what you need, there can be an extension that you develop or someone else develops that may have those features. And really, I think the biggest point here is that when you hear standardization, it's not constraints. We don't want people to feel constrained. It's really being designed to be flexible for any future changes or developments that come out.
30 seconds.
And I'm going to hand it back to Tam.
Sure, if we're pressed for time, so real quick, I'll just run through some of these videos in here. I hope they're running. Yeah, so just wanted to share some real world experience to you all. We saw an experience from Michael earlier as well, but really what Gaussian Splat allows you to do in Geospatial is this 7 things that we have on the slide. Highly realistic scene representation, detailed rendering of complex structures, not achievable in traditional photography. That's key. It's also cross industry, as we said, and then also modeling vegetation and really high detail is also possible now. And all this ties up it being available as an open format, and really we're excited in Geospatial to leverage this new technique for rendering 3D scenes. And right here, the last slide that we have is maybe a good call to action. Jason.
Yeah, this is just, we want feedback, we want collaboration. You can follow that QR code, read the proposal we have. We welcome the feedback and critiques, and we want to make it as best as we can.
Awesome. It's super exciting to see Esri, Cesium, and Spatial working together on the geospatial side and doing this in just a collaborative way, looking for feedback across the industry. And yeah, all the value prop there for Gaussian Splats or Geospatial is big. So next up, folks, when we look at Gaussian Splats, there's been so much innovation for folks that are doing engines on the web. And the Babylon team has a long history of leading 3D on the web, and we're going to hear from Cedric about what they're doing with Gaussian Splats.
So today I will present you a use case of Gaussian splatting on the web using Babylon.js. Babylon.js is an open source 3D engine featuring most of web technologies available, like web GPU, advanced audio, mobile support, etc. It consists in a runtime engine and a set of tools like animation editor, cell inspector, node material editor, sandbox, etc. All on the web and freely accessible. When Gaussian splatting was announced, it was certain we would integrate it into Babylon. The engine uses standard technology stacks like glTF for geometry, PLY, SPZ for JS, OpenVIA. Philosophy of Babylon.js is ease of use and deployment and fast iteration. Our goal is to democratize 3D on the web. Gaussian splatting is an important feature because of the ease of capture and display. And this presentation is a use case of Gaussian splatting on the web for a digital replica of St. Peter Basilica in Vatican City. The project involved many teams, and we had the chance to work on rendering. Different files formats were evaluated, and we finished by using SPZ. It supports spherical harmonics, and footprint is among the lowest. Also, a C++ library is provided by Niantic to make a conversion between PLY and SPZ. We used it as a reference implementation, and we made a TypeScript bottom. It's easy to miss a space or color conversion, like with spherical harmonics conversion, for example. You can see specular, but you'll have to rotate the camera to see it behaving badly if you miss the implementation. It can be easy to miss in the St. Peter Basilica replica, as it's a full experience, and it needed careful integration of data. The St. Peter Basilica replica is a full web experience, as I said, and it needed also standard geometry rendering. So the use of Babylon allowed it to mix with the rest of the engine, and it was a big plus. It's possible to render some part of the scene using glTF for some backgrounds, for example, while keeping the center of interest as the Gaussian splatting. Camera animation paths are handled by Babylon, and post-processing inputs and other features are also provided by the engine. So I wanted to show you two quick videos. This was rendered in a web browser, and there are between 3 and 5 billion splats. Each splat is sorted on the CPU using a web worker. And another one that shows many details. I'll give you the link later to that web experiment, so you can check it by yourself. Thanks to this project, we learned that it's possible to make valuable experience on the web using Gaussian splatting. The coordinate system and color space led to some back and forth with the team responsible for content creation. Data compression, encoding make the file size easily distributed for the web. There are recent advances in data storage like SOGS that we are evaluating. A few mistakes and bugs could be caught earlier during development if we had good comparison and better test suites. It's easy to mix spherical harmonics conversion, for example. Whether it's the assets or the shader that we are developing, the sooner the bug is detected, the faster it gets fixed. Most of issues were solved by comparing our renderings with other engines. Sometimes transcoding the data to an intermediate format was needed and would bring its load of numbers. Other easy mistake is left-right issues when everything is rendered symmetrical because of bad conversion of position. At the end, the experience was great and shows it's possible to have rich and detailed Gaussian splatting on the web. It's also possible to keep the footprint under control thanks to quantization and compression. It's already usable in production, even on mobile. So it needs for standard. Maybe first thing needed in the first standard is the coordinate system. Is it left hand or right hand? What is up, etc. These have implications on splat position, scaling, and orientation. Secondly, we need information on how the Gaussian splatting has been trained. So it's possible to tweak the rendering accordingly. Properties like kernel size and compensation depend on that. And no standard verification is available at the moment, so we need a reference Gaussian splatting scene and rendered image for comparison of the render. With different parameters, different training, different compression, normalization schemes to improve the compatibility. And that is useful during development, validation, and debug. So before ending this presentation, I'll give you some links to test and evaluate Gaussian splatting on the web. First, it's obviously the St. Peter Basilica visit. It's a web experiment that you can visit, and I'm sure you will get many information and things you didn't know before. And the second link is a documentation page for playgrounds using Gaussian splatting with Babylon.js. It's possible to experiment, share your scenes with Babylon.js. It's really easy. It's also possible to create the Gaussian splatting from scratch and understand how splats parameters like orientation and size affect rendering. Or it's even possible to generate a Gaussian splatting fully procedurally. So you can, for example, stream data from one web server to the client world. Have fun experimenting with Babylon.js. Thank you.
Great presentation. Thank you again, Cedric. And thank you for all the open source contributions you're making, right? As we advance the field, as we experiment with open source, it's key to that collaboration. And interesting to hear about the good performance you're making as well. So folks, when a new technology comes out, you really look for those more key use cases. In the early days of reading on the web, the New York Times, one of the early adopters, really showing how useful it could be with journalism, and we're at it again with Gaussian Splats. So we're going to hear from AJ. AJ?
Hi everyone. I'm AJ, and I'm going to talk about our Gaussian splat exploration. So don't worry, these QR codes will come back at the end. But if anyone wants to grab some of the look grab a look at some of the work that I might be referencing, you can go ahead and do that now. So a little bit about our R&D team. A lot of people, when they hear New York Times R&D, the first thing they say is the New York Times has an R&D team. Yes, we do. Different than some other R&D teams, we're generally looking about 6 to 18 months out, right? We're not looking 10 years in the future. We're looking for things at the intersection of technology, journalism, and storytelling that are actionable for us in a shorter term. So our exploration, we first published about a year ago. So if that gives you a sense of where we might be in terms of publishing something with Splats, no promises there. But the reason our R&D team exists is to explore these technologies before the newsroom is using them, so that when there's an opportunity for the newsroom to use Gaussian splatting, we already have the workflows in place and the technology in place to make that simple for them. So, in brief, our exploration focused on a couple different axes. We were looking at what is the simplest, most lightweight, easiest way to make a splat, sort of the minimum viable product, and what are the edges of that, right? Where does it really start to fall apart? And additionally, with our highest resolution cameras, lots of people, controlled environment for the capture, and a ton of render compute, what's sort of the highest quality that we can do? And in testing both of those, what we end up doing is trying a ton of different cameras, from mobile phone capture, action camera capture, mirrorless, DSLR, medium format, digital, all sorts of things for quality, multiple camera rigs, multiple person rigs. And this lets us sort of figure out the edges of the technology, like I referenced before, right? Where do things fall apart, and where do we sort of hit a maximum sort of resolution or quality for what we're putting in, right? Where do we not need to worry so much about that return? So why splatting? Well, the same reasons that everyone else here is interested in it. photorealism, view-dependent effects, but also the speed and ease of capture and rendering, right? The New York Times is a very large organization, but most of us are not technologists. My route into R&D was with over a decade in the field as a documentary video and photojournalist, right? So the people most likely to do splatting for us are not technologists who are comfortable with like the rendering pipeline. They are journalists or visual journalists who are comfortable behind cameras or even just comfortable with their phone and willing to try something new, right? And as Patrick alluded, we've been publishing more and more spatial journalism over the years. So with that, all of the things that splatting brings, the speed, the ease, the photorealism, all of these things become more and more important the more we're publishing stories like this. But there's also some concerns and considerations that we're taking into account here. So when we've done spatial stories before, we've used photogrammetry or we've used just models of existing geometry, right, that are just painted white with soft light. When we're working with splatting, we can no longer point at sort of a pixel on a mesh and trace that back to an original photograph, right, because of the way that splatting works. So we want to be able to signal this to our readers, right, that this is not constructed of photographs, but rather was constructed with the information from those photographs, right? And also as journalists, with transparency and accuracy being the most important things for us at the Times, we want to make sure that if we're seeing an issue in one of our models, right, we need to be able to trace back an issue to that source image, right, in a different way than we would be doing it with photogrammetry. So, I'll try and speed up a little bit because I know I tend to talk quite a bit. But we found a number of things in this. We confirmed a lot of what we already knew from our photogrammetry captures, that we could use multi-camera rigs really easily, that we would get better rendering quality on all of the things folks have already talked about, transparency, vegetation, air. But a couple things that we found that were surprising and really useful for us is that you can actually do quite a bit with splats from sparse or truncated source footage. Why is that interesting for us? Well, I'll come back to it in a little bit, but sometimes we're working with source footage that was not even collected by a journalist, right? Or was not collected with the intention of a 3D model being created from it. Additionally, we did some experimentation with stylization, both before, so rendering or stylizing your source images, and also afterwards, stylizing the splat after it has been created. Why are we interested in that? Well, we want to signal to readers, right, that we are using something virtual. So stylization is sort of a shortcut, a way for us to use a visual grammar to let people know, hey, what you're looking at is as accurate as we can get it, and we are verifying it and vouching for it, but we need to be transparent with you and let you know that this is coming, this is a render that we have created, right? So let's back up for a bit and talk about how the Times builds 3D stories. So in collaboration with the Newsroom Graphics Desk, I think some of my graphics colleagues are in the room today. Thank you for supporting me. But we have an internal tool called 3Bird, and I will emphasize it is internal because folks like to ask me a lot, how do I use 3Bird? But 3Bird is an internal tool that we use for our current spatial and 3D storytelling. We've published a variety of stories here, a walk down a historic street in Chinatown. We've used computer vision models to extract athletes' bodies from still photograph, turn those into 3D models and do explorations of that sport. And so the first step when we were experimenting with splatting in this pipeline was how do we get splats to work in 3Bird? So some things that we've done previously in 3Bird, right? This on the top, you're seeing the Miami condo collapse from a couple years back. So to tell this story, we used sparse drone footage that was collected at the scene to create a partial ambient occluded model of the scene. So this is an actual use case that we would be considering, could we do this with splatting instead of with photogrammetry, right? What you're seeing at the bottom is B-roll, or rather a splat of Aconcagua, which is a glacier on a mountain in South America, that was reconstructed with B-roll used in a documentary about this location. And again, crucially, this B-roll was not collected for the purposes of making a model. So you'll see there's a lot of artifacting and a lot of issues in that model, but also you'll see that there are sections of it that are very, very usable, right? One of the things that I think folks here would probably understand is when you're doing a splat, that movement virtually along the real life camera path that you did for the capture is one of your most viable recreation viewpoints, right? So if you've got some sparse footage or found footage that's very shaky, but you're trying to walk people through it because it's important, splatting is a way that you can kind of stabilize that footage, right? And so we're not using a full 3D model in that scenario, but it's a potential use case that we can really elucidate some complex spatial storytelling with. 30 seconds, thank you. So just to wrap up really quick, other ways that we're thinking of incorporating splatting, we support Cesium tiles in our 3Bird program. This is an experiment with combining that with splatting. We get higher fidelity here, we're able to anchor this in real world context and again connect it to that ground truth. Some examples here of stylization as a signal. Previous examples that we've done with stylizing clouds and some ways that we might think about animating in splatting to let people know what they're looking at. And lastly, as we think about standardization, how do we interact with splats? How do we get geometry from splats? Often we're doing visual forensic stories. So real world proportions and sizes are key to that, right? So how do we ensure that our splats are accurately sized? And how do we make sure that we can deliver these not just on a really powerful computer, but to people that are maybe in parts of the world with really poor internet connection that are on a cell phone that is several years old, right? A lot of our audience is not the people in this room. A lot of our audience is not even similar to the people inside the Times building, right? People are accessing our work all over the world, and they're accessing it primarily on phones and primarily on poor internet connections. So, the ease of delivery, the speed of delivery, and the smaller size of splatting models, I think really position them to be quite useful for this in the future. And I know that I'm probably right about time. Thanks.
AJ, great presentation. And look, it's really interesting. We have researchers, practitioners, and then users who are all advanced in that field together. So getting those insights for the benefits of journalism is really valuable. Great to hear again the mobile theme you also heard from Cedric. And AJ wrote an awesome article too on Gaussian Splats. This is linked from right here. So I encourage everyone to read that as well. So folks, next up, we're going to go a little deeper on Gaussian splat representation. We're doing it meta, and even some insights around animation and volumetric representations. So please welcome Nemanja.
Hello everyone. So my name is Nemanja, and I'll present to you what we have in meta in terms of Gaussian splat representations and how we're actually using this to achieve some of our product visions. So I'm a software engineer in the codec avatars team, mostly focusing on rendering, runtime, and optimizations. And I'm also the author of our internal Gaussian splatting engine that we've used not just for codec avatars, but also for environment scenes and other kinds of applications. And I guess that's where our first slide starts. I want to first mention the product that we're currently building, and one of them we already launched last year is a tech demo. You may have seen it or tried it. If you have a quest, you can already do this. It's called Hyperscape, and it features a couple of high-quality reconstructions with some indoor environments made from some famous artist studios who have a lot of colors and variation and interesting things to look at. And it was our first foray into seeing how we can use Gaussian for different products. And from then on, we realized that if we want to really deliver on this vision of immersive telepresence, VR, AR, or some other kind of medium hardware for codec avatars, we want to enhance these spaces where we can see these avatars with realistic spaces as well, right? So we bring, for example, you can scan your own apartment and then send it over to your friend. You can then see it, perceive it, and then render that environment as well as your own avatar, so you can communicate with this virtual environment. And this is basically the main premise of why we're trying to kind of code all these things together and have them interoperate relatively well, right? So we don't want to just have them as a separate things on their own, even though it is still perfectly feasible. And for us, Gaussian splatting representations come in many different shapes and forms. Some of them are compressed in different ways. Some of them are generated at runtime using these so-called decoders, right, for the avatars themselves. And different representations necessitate different kind of pre-processing steps, right? You can have animated Gaussians, static Gaussians, dynamic 3D video kind of Gaussians that is now exploding in research as well. And all these things have to be efficiently handled. And for all of them, typically we have a different representation, both in the file asset and both in how we process and deliver them at runtime, to to make them actually like work and render both on standalone devices and also like huge cloud workstation GPUs. And besides just like the representation itself, or whether we can skin some Gaussians and use them as a character or visualize environments, we also want to embellish the things with different per Gaussian attributes, like we actually have some sort of a relightability, whatever that means for this kind of representation, as well as to make it more relatable. And most of the experiences that we're trying to build are meant to like coexist with each other. So we have our unified Gaussian Splatting engine is able to take those different models and then process them independently and then merge them into a global rasterization. So you have no need to really do some sort of depth compositing, just kind of splat all the Gaussians together. And these experiences can both happen, you can render them on the cloud or you can render them on your device with some quality caveats because of the hardware limitations. But the idea is that for both cases, you will need to have efficient file format, right? Something that efficiently translates the files from one place to the other without you having to wait for minutes or hours to get your file at the end to actually display. And this is kind of where we want to start with our file format considerations that we have internally. Basically, the topmost priority, I believe, is the compression. We need to deliver the assets quickly. This is like a cornerstone feature of most typical mesh-based pipelines, where there's already like an LOD system in place. So there's that, but you also, to deliver the highest LOD, you shouldn't have to wait forever. And with huge files that this technology has started, like PLYs, they were huge because none of the attributes were actually compressed. They were all 32-bit floats. There's a lot of them per Gaussian, up to like 240 bytes or so. And when you have at least 500,000 Gaussian splat seen, possibly even more, these files can be like half a gigabyte, gigabytes, how large, right? So until you actually get them and see them, maybe the user has lost interest because they're just scrolling through a bunch of things. So the idea is that the compression techniques developed by Niantic and then Cesium to create this SPZ file format are actually very handy. And we took this a bit further internally and then added a bunch of different kind of compression things like codebook compressions, or maybe experiment a bit with different color spaces because some of them compress better than others. And ideally, this can all be kind of standardized and used because at the end of the day, what we're doing is we have a JSON and some binary files, and that's basically glTF for the most part. Other stuff that's going to come up, and it's very important as well to us and interesting meta, is these dynamic splats, right? These 40GF splats based on Gaussians and all these other kind of similar technologies that are being developed. The idea is that you want to create an immersive. You have some video and you want to observe from any kind of viewpoint. And most of the samples you see today are like 10 seconds long, 20 seconds, maybe a minute, maybe. And the idea is to really like make this work for full feature films, 20-minute videos, 2-hour videos, and when you look at the uncompressed data required for that, even if you could write optimization, optimize all that, it will be ready. You're looking at like 20 terabytes of data. That's infeasible. You don't share this with anyone. So to bring this down to some sort of manageable storage file size, you can apply the SPZ, let's say, natively without any sort of temporal compression. You get 90% compression rate. You go down to like 2 terabytes, still very large. No one's going to download this on a mobile phone. Even storage, right? The phones don't even have it. That don't have such high storage. So you want to have, let's say, a 50 gigabyte file. That's kind of still too huge, but getting into a territory of manageable. So you would have to have like a compression rate of at least 99.8%, if I calculate it correctly for the baseline. That's huge, but the good thing is that there's a lot of research and R&D interest happening here. So most likely we will be having some sort of a standalone video codecs, kind of 3D Gaussian codecs just to handle the animation and the streaming part of that. Other stuff that's fairly important to us is an additional metadata that you use to render the scene. So it's in the name that the Gaussian splatting is going to probably use the Gaussian kernel for the actual fall-off of each splat, but that's not always the case. In the case of Hyperscape specifically, we are actually using quadratic functions, right? So if I give you the file today, you will never be able to open it anywhere. It will always look bad. It has all the same properties, scale, opacity, Lagrangian position, but just look a little bit off, right? All the edges will be a bit weird and so on. So embedding this kind of information into the file format itself, as well as metadata of how this kernel function is shaped, is relatively important for interchange. And the reason why we, for example, use quadratics is because on mobile, you probably know that performance of exponential functions is very, very slow. And the quality difference that we found were there were no real quality changes trying to switch from one to the other. But of course, you have to train it with this new kernel as well. And of course, other stuff. You have stacker harmonics that can be in HDR if you're trying to do some advanced post-processing later. Sorting logic can also change and so on. Yeah. And for the last slide, besides just the baseline like representation of radiance inside Gaussian splats, a lot of effort is going into making these things function beyond just like standalone scene. You want to make maybe Gaussian splatting a first-class citizen in your engine, and that brings a whole lot of problems that you just didn't know existed before. So you want to, for example, have some sort of a depth or composition with other transparent objects. That gets very tricky very fast. You want to have relighting. It's also very tricky because the material and the light isn't angled inside each Gaussian with vapor harmonics. And you want to have support for that kind of stuff like procedural animation. For example, imagine a forest. It's like nothing is moving. It's kind of dead. It's interesting for a while, but then you kind of want the leaves to move. You want something to hear something separate from that. Yeah. The point is that procedural animation, other kinds of animations are interesting. You could build like building blocks for 3D GIFs in AR space and VR spaces, and so on. And this doesn't have to be part of the first version, the standardization, but something that should be added naturally in the future. I think that's it. Thank you.
Once again, another great presentation, and I love the focus on the size of the splats and the need for compression and LEDs, and also this pragmatic approach to what can be standardized now, and what are some longer-term improves like compression. All right, folks, so next up, we're going to hear about reaching developers of Gaussian splats from our folks at Spark, Christoph and Andreas. One.
Hi everyone, we're Andreas, the lead developer of Spark, and I'm Christoph, developer of the pulsar renderer, one of the precursors for Gaussian splatting. There's lots of splatting that have Gaussians at the time. We are both currently working at World Labs and creating models to create entire worlds as Gaussians. That's why we developed the Spark renderer as a way for people to share these worlds on the web. And we really need that as a way for sharing this content across as many devices as possible. So Spark is built on Three.js and WebGL2, which is really, really widely available today, and runs nearly anywhere. It is completely open source, so you can use it for any project in any way that you would like. It's really, really simple to use. You can literally just add a single line to your code, add splats to your SIGGRAPH, and you're off to the races. Overall, Spark has a lot of unique features that really set it apart at the moment and make it future-proof, and we'll see where we can take it. Today, in particular, we want to look closer at the user programmable shader graph system that can be used for modifying or animating splats, and all of that happening on GPU and very, very quickly. Let's have a quick look at the render cycle overview in Spark. So given a set of splat objects, we first aggregate them into one unified coordinate system. Then we sort them on the CPU altogether for each of possibly multiple viewpoints, and then we render them for the respective views. Because of this first step, this aggregation step, we can automatically apply additional transforms or modifications directly, which means that you can even do skeletal animation on the GPU as part of the executable shader graphs. With that, I'll pass it on to Andreas, who will talk in more detail about this.
Thanks, Christoph. So, for those of you that are not familiar, a shader graph actually refers to this type of system that you might see in Blender. where you have nodes that essentially express some sort of computation, and then edges that connect the inputs and outputs. So you can kind of form like a computation graph from this. You can also express these graphs in code, as I'll show you in a sec. Now, Spark actually uses a shader graph system as a core component of how it's built. We call these nodes dynos, and they can have multiple inputs that are typed and multiple outputs that are typed. And each of these types can be any GLSL type, but they can also be compound user-definable types, like a G-splat that contains all the properties of a Gaussian splat. If you use Spark or TypeScript, you'll even see in your editor if all the types match up between the blocks. You can write your own dynos using just plain GLSL code. So GLSL, by the way, is just a shader language that WebGL uses. But you can also create dynos that are modules, where you recursively include other dynos and wire them together to create something more complex. Spark will take a graph of dynos, convert it to a GLSL program, and then that will be compiled to run on the GPU. And Spark even comes with a pretty big library of dynos that you can use right away. So there are low-level dynos that essentially cover one-to-one all the different built-in GLSL types and functions. But it also comes with a bunch of high-level dynos that make it more convenient to work with things at a higher level. So for example, it's more convenient to work with Gaussian Splats using some of these dynos. You can also work with signed distance fields. You can hash inputs to create random values. You can recolor your splats any way you want. Now, the core component in Spark that uses this shader graph dyno is called a splat generator. You can have multiple of them in the scene. And the goal of the splat generator is to every single frame regenerate all the splats. And it does so by essentially assigning a dyno to each splat generator. And it takes as input the index of which splat it should generate, and as output, it produces all the different splats that you want in your scene. So the center, the color, the scales, all that. But you can also pass in any other inputs you want. So for example, if you pass in time as an input, you can create a time-varying animation. Or you can pass in textures to look up any data you want as part of this computation. Now, usually you'll probably use a higher level concept called the splat mesh. Now, it's just a subclass of the splat generator, so it also takes an index as input. At the very bottom of this long pipeline, it produces a Gaussian splat. The difference, one of the crucial differences from a splat generator is that it takes essentially a template of splats. So like those butterflies you saw earlier. Each of those uses the index to pick out and read each splat and then pass it down this pipeline. So you can see the second box there, for example, takes the view direction and spherical harmonics data to evaluate the directional lighting and adds that to the color of the G-splat. So you see there's like skeletal animation in there, there's also like recoloring stuff, you can do relighting in there, but crucially there's also 2 places you can insert these user modifiers. And the modifier is essentially your own dyno that takes a splat as input and modifies it any way you want to kind of change it, animate it, whatever you want. So I'm going to finish with a couple of examples. And in the bottom here, you can kind of see that there's this butterfly that's shaded by z-depth. And this code here shows you exactly how to do that in Spark. Essentially, it has things like the view transform, minimum, maximum z-depth. And from that, it creates a graph of dynos that you can see first picks out the center coordinate, transforms that to view space, then picks out the z-coordinate from that, and so on, and finally assigns that normalized depth to the red, green, and blue values. And that's how you get this like different shades of gray depending on the z-depth. Oops, missing that. Run these again. Can't play it. That's unfortunate. Well, anyway, so you can see there's also another splat there that had like different coloring at the same time, and hopefully you enjoyed some of those other interesting transitions and effects that we had going on there. So anyway, that's it. Hopefully we've shown you that Spark kind of goes beyond what you might expect from a 3DGS renderer. We built it to be dynamic, flexible, but most importantly, user programmable. And we hope that some of you will maybe create some really cool online 3DGS experiences. Thank you.
Andreas, Christoph, awesome work, and your timing was like perfect to the second. Really great to see that you're you're doing open source, you're doing on the web, you're doing cross device, and yeah, this concept of bringing a shader graph and Gaussian splats together, I think is really cool. So folks, next up, I think everyone has heard of. All right. So folks, I think everyone has heard of NVIDIA doing a lot of great work with physical AI. So we're going to hear from Nick about that, but also Gaussian Splatting with USD. So Nick, welcome.
So, hello everyone, I'm Nick. I'm leading a team that brings all of the great research on 3D Gaussian splatting that NVIDIA has done into products that are experienceable by the community. And today I'm going to speak about exactly that, right? So how can we enable physical AI by providing highly realistic simulations, and to discuss with you together the question whether or not we are ready for standardization. So, but first let me start with an example and a bit of an explanation about what Gaussian splatting is. And we talked a lot about it today already, so I want to give you a bit of another perspective that you can take to your kids and family or friends. So, for me, this is actually a real story from a recent weekend in my garden. I was sitting there together with my wife and kids, and they were asking me, so what are you actually doing at work? And I said, well, okay, I'll try to explain it in a very simple way. Let's imagine you would paint a picture of where you're sitting right now, but you don't draw it with pens and a canvas, right? But you would draw that picture using balloons. So basically you would attach a set of balloons and some nails that are placed on a wooden board. And you would use different shapes and colors of the balloons. So if you put up enough balloons, you would end up with a nice picture, which would roughly represent actually the view that you're seeing right now. So the grass and sky, right, from that perspective. My son actually started doing that directly, and after 4 balloons, he was already like, well, Dad, that's exhausting. And it takes a long time, and I said, yeah, right, that's great. You now understood that runtime correlation and the amount of balloons we have. So he went on and said, yeah, but those 4 balloons actually don't really represent like that garden here. And I said, yes, that's another good observation. So we need a lot of balloons actually to make a good reconstruction. So we went on, and at one point we went out of nails. And he said, okay, what should we do now? And I said, I don't know. You just like experience right now what it is about like running out of memory. So we looked at our balloons, and my son was very happy with it. But I said to him, well, that looks great actually from your perspective right now, but it doesn't look so great from my perspective. So we arranged them together that it fits more both of our views, and that is what I explained to him is what we call optimization. So in a very simplistic way, this is what Gaussian splatting does. Instead of balloons, we're trying to optimize the positions, scale, color, rotations of Gaussians to then use them later to project them and render an image. And we use the actual images to calculate the loss, which is backpropagated then to the Gaussians. The original paper, as we heard earlier, was introduced here at SIGGRAPH in 2023. So how can we make use of Gaussians to enable physical AI? AI needs an environment where it can actually be trained and tested safely. For this, we bring the real world into simulation using Gaussians. The process for that is to take sparse observations from a scene and actually then train a reconstruction model. We can then query this model for novel views, which allows us an example to render a 360-degree view of that scene. And for robotic applications, this is a key feature as we can now simulate novel camera paths, and it allows us to test different sensors or other sensor setups from different like mounting positions, as you can see in the video below. To bring the real world into simulation, NVIDIA has just announced Omniverse NeuRec, a set of APIs and libraries to generate interactive 3D simulations from real-world data. And it includes reconstruction, rendering, and generative models to enhance really the fidelity of those simulations. For reconstructions, NeuRec leverages Gaussians to reconstruct scenes into millions of particles that can be moved and manipulated. For rendering, we add ray tracing to improve the fidelity of the reconstruction using our 3D GRET rendering algorithm. And finally, generated models fill in reconstruction artifacts for high-quality novel view synthesis. So what's important here, right? We are rendering from completely null views that we haven't seen during reconstruction. This is very challenging. Generative models really allow us to fill the gaps here. NVIDIA uses USD as a way to store Gaussians. Currently, there's no real industry standard for Gaussians, and the field is still evolving rapidly, as we heard, right? So this makes standardization really challenging. When talking about standards, it is important, Michael pointed that out already earlier, to consider that if it is too rigid, innovation might become slow. If it is too loose, however, there's no real point in having a standard, right? So at this point, we believe that extensibility is the key to a good standard, and we are really looking forward to work together with the community to define a suitable standard. Why is standardization important? Standardization allows us to reuse the reconstructions in basically any open source applications. We have just recently enabled Neural rendering in open frameworks like Kala and ISA. For Kala, we reconstructed over 80 different scenarios and made available via Hugging Face. This allows any developer to test AV applications and simulations on real-world Gaussian splatting data. We encourage the community to engage with those and use it for replay-based testing. Similarly to Kala, also iSigSim 5 now comes with Gaussian splatting and 3D-QT support. So using the publicly available 3D-QT repository, you can record any real-world environment and turn it into a simulation where you can place a robot and let it interact with the environment. I'm really looking forward how researchers and engineers interact with the real-world scenarios that have been brought into simulation and how this drives our goal forward to enable physical AI. Thank you.
Some really impressive work, and I love the balloon analogy. I think we're all going to use that as our big intro for Gaussian Splats. So folks, I'd like to do a few rounds of applause, and then we're going to do Q&A. First, a lot of people helped put this together today, so I'm going to do a round of applause for Lucy, for Neil, for Amanda Morgan, for Tim Lewis. Next up, all of our presenters, they were on time and they were prepared. Like the slides were done yesterday. So in addition to the great technical work they're doing, they did really great presentation work. So give a round of applause for all of them. All right, folks. So for Q&A, I'm going to run a mic for our presenters to answer questions. Neil, are you going to run a mic for folks who want to ask questions? There's also a mic, and if it's easy for you to get up and use the mic in the middle right there, is that working? Once we have that one working, we'll use that. Otherwise, Neil will be running across the room. So let's just open it up broadly with who has the first question.
Well, I'll start. So there were a lot of people taking pictures of all the QR codes and various slides in the presentations. How are people going to find out where the information is available?
Neil, you want to answer that?
It's all be posted on the Netherlands Standards Forum webpage. So use standards.org with the hyphen, and you'll see it. Go to the events tab, and you'll see the SIGGRAPH page. It'll all be posted there.
And I'll leave that up for a second for folks. All right, who has the next
question?
Yep.
Yeah, thank you. Amazing presentation. So my question is around, so I'm in the film industry, we're using splatting, and obviously colour space is really important for us. I was wondering, if any of you had any thoughts or kind of are working on kind of colour space standardization and how that might work.
Yeah, good question. Any of the presenters want to talk colour space? New York Times looking at that by chance?
So we're not working necessarily with the color science, right, of matching our images to logs, but if you take a look, if anyone here wants to search for the New York Times Diversity Plaza 3D story that we did, that was something where we created a photogrammetry model from source images and then also had a photojournalist there doing on-scene reporting. And so matching the tone of our grammetry model to the images that we were using to transition in and out of it was really key and really difficult. I think a couple things that we've learned for consistency in your color is starting with raw images or log video and doing a pre-production pass to get it in the general space. And then if you're comping something together, I would really recommend like doing a splat as like a first pass, comping it into your work, and then like doing your final color pass in your work, and then maybe re-rendering the splat with new color information before comping.
Mark, you want to add it?
Sure, yeah. And so to give another example too, I don't know if you saw, there's a commercial called We Know Good Food coming out of Australia, and the VFX team actually posted a really long like workflow documentation of still remaining in, you know, to retain all the color space that they needed for it, where they were using I think like 32-bit EXR to post shot, and then going back from like new to Houdini and then back into like post shot again. That worked, and I believe that Belayneh also has a way to retain, like, let's say, like the ACES color space as well in their suite. Oh, and the post on LinkedIn as well. The guy's name is Matt Burns.
Another question over here. But can I suggest that the speakers that they're answering stand up a bit?
Yeah.
The podium, because we're doing a video and the audience can see you. That would be cool.
Hello, I have a question. Is there any current or upcoming solution for the tileable loading, or I would say delayed loading of the splats? So let's say for VR usage or web usage, so real-time streaming, pixel streaming based on the delayed loading of the splats. So I mean, think of the game level and you like loading the splats upon you moving to the
Anyone with you?
I mean, it relates to compression, right, as well.
Yeah. I just go to the podium.
Yes, right. So, question is about delay loading, and traditionally, at least in the geospatial space, how we've done it was wrap it around formats such as 3D tiles that will handle a little bit of detail, so that you can swap in, swap out different representation of the same object, so that you can scale it up. I think with Gaussian Splats, the same kind of technique could work here, but necessarily not having it in one asset, in one 3D asset, if you will, but being able to swap out and swap the switch out with a different representation. So those are the kind of things that, at least in Geospatial, that we could look at.
Yeah, I saw the implementation for the meshes in Cesium. Are you guys working on anything?
Yeah, so the idea is using a similar kind of concept to be able to, you know, swap in, swap out different representation of the same object with higher fidelity. And this is where the beauty of using, you know, 3D tiles and other representations comes into. The bounding volume is already defined, is already available, and you can use those, you know, primitives that we already have to be able to do that. So yes, that's something that we're all actively looking at.
Is that really open source? Or
of course. Of course.
Cool, next time. Another question, Neil, we have a question right here.
Yeah.
And then Adam, and then from bottom in the back.
Thank you very much. I would go up there, but it's a little tall for me. So with regards to the NVIDIA guys, you were talking about some generative tools to fill in the blanks for splats that aren't quite, there's not much data there. I'm just wondering, is that something that, like the data, is it derived from the stuff that you captured, or is this based on like an LLM or something?
That's a good question. So typically you have real input data. So imagine, for example, you have an autonomous vehicle driving down the road. You would just take exactly those images that the vehicle has recorded, right? But in simulation, you want to go now like one lane to the left and simulate how a drive would look like from there. But now you're basically really lacking some of the information, some of the viewpoints that you want to render.
Okay, cool. So is this like run locally, or do you need, internet?
No, we basically have the recordings available. We load them down into the training, right, of the Gaussians that we're basically deriving from there. And when I was talking about the generative models and why it is so important is if you use Gaussian splatting in the standard application as it is, right, you are really bound to this input data. Now you can add a lot of regularization because you know, for example, the ground is flat, and you can try to tweak your Gaussians like that. But it typically is very challenging actually to do that. So if you use additional content from models that have seen the world, so for example, the Cosmos models that we use to actually then enhance this data, they have seen millions of data and video footages, right? And we can use that context to then use generative models to enhance that reconstruction because they have seen the world and know how physics work. So basically, this is a way how I see actually the future is combining generative models with Gaussian splatting techniques to get a really good and well-grounded physical representation out of that.
Okay, thank you.
So Adam, you have a question? And then there's a question all the way to the back.
Yeah, so I am actually one of the co-authors with Tam and Jason of the glTF extension, and I've also been working closely with the AOUSD folks. And I think an open question that maybe we have for all the presenters and kind of everyone here too is if there is metadata that you need for rendering, like I know that Meta showed some of that, it would be wonderful if you could actually tell us that. Because we want to actually incorporate that in both proposals for USD and for glTF. So I know that I don't know if the AOUSD guys are here right now, but yeah, this would be. Yeah, it drift. Yeah, so it would be wonderful if you guys could share that with us. So thank you.
Yeah, definitely talk to Adam. But does anyone want to share a perspective on that? Yeah. Related to that? Or?
No, different.
Oh, okay. All right, well, let's go to in the back.
Hi, Mike Lassner with FireScore AI and we're working with Wildfire. Data gathering using drones, including multispectral and hyperspectral drones. And so my question is basically, maybe for the Esri folks, but also for anyone else who's thought about it, how does multispectral or more than RGB anyway fit into this? And there are a bunch of papers out there on Gaussian Splats for that, but is that part of the standardization thoughts and efforts at this point, or should it be?
Geospatial person, I appreciate you asking. Tam, do you want to?
Sure. Thank you. Well, I'm glad you asked that question actually, and there were folks that were asking similarly that the visible spectrum is not the only thing that, especially in that kind of situation, for assessment. One thing I would say is that, well, right now there isn't anything on the table to capture that, but at the same time, I would say there's nothing else that would prevent it from being able to be captured in this structure that we have. Similar to with point clouds, where you can have all kind of attributes captured within that primitive. It's the same idea here. There isn't nothing per se that would be limiting it from capturing any spectral data. It's just that the current widely available content comes from imagery, from visible imagery, and that's why we have that. But definitely that's an area that we would love to expand it to it, because if it is good for the goose, why not for you know how the expression goes. Like there's no reason why spectral data cannot be captured in this medium.
Cool. So Tam, we'll see a presentation at SIGGRAPH next year. All right. I think we have a question over here. Right here. Thanks. Wrong one there.
Thanks. All the examples that have been shown today, I think, were deriving the Gaussian splat from input images to the images. So I was wondering, as a question, maybe for all presenters or even to the entire room, if you're aware of any solution using traditional 3D assets and high quality render to actually derive from that as an input and sort of bake that high quality information into the Gaussian for rendering.
One, did you want to take that one?
Briefly.
All right, maybe we'll start with you and see if one other person will have an answer as well. It's really a question. Yeah, come on up.
So I know there was actually one of the footnotes in one of the presenters' slides, but there is a repo from EA that does mesh to splat, and it, I believe, still preserves the attributes and makes it, it's really, really fast too. Like it converts it in like half a second or something from mesh to splat, and then you can relight it still and do a lot of very cool things with it. But you can also place just traditional like synthetic cameras as well through a traditional 3D model, which is actually, I've seen a couple people in AEC start to do that now, rather than sending a very large file, of traditional 3D structure. They're just splatting it and then sending that instead.
Excuse me, repeat again. Do you have a link for this paper, or like what is this?
It's called Mesh to Splat, and it's from Electronic Arts. I would just search Electronic Arts, Mesh to Splat GitHub. I also have two other articles as well somewhere.
Cool. Did anyone else want to respond to that? That's really good. Thank you. All right, other questions? Provide the mic over. I'm right behind you.
Thank you. My question is mostly for AJ. In regards to your R&D and research, did you find that you had to kind of consider iterations and training time to meet broadcast deadlines?
Absolutely, yeah. So, a couple things. One of our big wins for us with the photogrammetry project was going from field to publish in under 2 weeks, right? Which for like a large scale piece of photogrammetry is, I think, pretty impressive for a newsroom to do. And splatting obviously lets us do that a lot faster. There's, in addition to the training steps, right? One of the things that we were trying to hone in on was sort of what's the minimum amount of training steps and at what point do we no longer need them. And we generally found out using post-shot in the 30 to 45,000 step range tended to be for our purposes, really, really good for both quality and time. But a lot of the testing that we did also focused on just commercially available tools like Polycam. And the Niantic tool, who's named Scaniverse, which is also really excellent. And those will turn you out models a lot faster, which we found really useful for internal purposes, right? This is maybe not publish ready, but this gets us a model fast enough that we can continue reporting and thinking about it and talking through it, and maybe go back and use some other affordances to make a much higher quality model.
Great. Quick second question, which was basically, how do you keep up with research and kind of day-to-day papers, and how does that factor in? Kind of an overall question for the rest of the panelists as well.
This is my first time at SIGGRAPH, and this is huge for me keeping up to speed with all this. A lot of it is just being immersed on, for me anyway, being immersed on these technologies in different corners of the internet and following up with people that I've met here that are doing cool things. Academic as well. I did a fellowship about a year ago, so I keep in touch with the academic folks that were doing some splatting and representation work as it relates to doc work.
Thank you for your talk.
Nice. Look, I really like that question. When you look at the pace that there was splats moving and the number of areas you might be able to see, I'd be curious if anyone else want to answer that question or how to keep it up. Michael, we can follow your blog here. Come on.
Yeah, so it's definitely a increasingly difficult problem, or a good problem to have. It's basically what I spend my entire day doing, is trying to stay up to date with the totality of the global progression of this technology. I would say that for me, I spend a lot of time going through GitHub and have a lot of email notifications set up across any of these things, and then just continuing to find specific people who are interested in the technology. And on the other side too, if anyone is currently working with the technology and wants to talk about it, please feel free to. I actually would encourage you to reach out as well, and I'd love to help bring people's work out into the world for more people to see. But yeah, I would say that as more industries and people and startups continue to come out of stealth, it's going to be continually more information at once.
Appreciate it. Thanks.
Michael, you're doing a good service for everyone in this room and across the industry. You're learning and sharing that, and I would encourage everyone to take my book on that opportunity to talk to you. So, additional questions?
So it's more of an open question to all the panelists, and I guess anyone else who's thinking about this, but a lot of the greater advancements that I keep seeing in radiance fields and Gaussian splats are usually hampered by restricted licensing. So some of the greatest things that I've seen come up are restricted license. They're things that I think should then eventually become part of the standard for something like Gaussian splats. But I'm not sure what the good path is over to that, whether, of course, if you've worked on something very new, you want to be able to profit from that, you need to be able to develop new things. But then if something becomes an open standard, at some point you have to let go of that and give it back to the community, which I understand is the point of this forum, but I just wanted to get people's perspective on that, because it's a challenge I run into quite a lot. So I'm a product manager working with a lot of this at the moment.
Yeah, look, it's a great question, and a lot of the folks who presented today, we're doing a lot of the source as well. So yeah, let's see if any of the speakers want to do it.
Could we actually, would it be okay if we had the speakers just come up so I could grab a picture too? If you guys don't mind.
All right, so we're gonna do a quick picture, and then we're gonna get some folks to answer that question.
Feel free to just answer the question. I'll just take a picture. Here we go.
Here's the right answer to the question.
Who wants to tackle it first?
Hello. So yeah, there are a couple of really great open source repositories right now. I think the three that would come to my mind off the bat would be Nerve Studio's Gsplat is definitely served a lot of implementations that are being powered around the world. The next one I think there's a pretty permissible license is actually the 3D GRUT from NVIDIA that has both the unscented transform and 3D Gaussian ray tracing in it. Those are both permissibly licensed, and the third one is Janusz, otherwise known as Mr. Nerf, has a Gaussian Splatting CUDA implementation as well, which is very permissibly licensed and is also being actively developed as well. So I would suggest perhaps one of those three.
No, I suppose the question's more when something new comes along and the community gets collective interest in this new technique, this new technology, how do we start to incorporate, this might be a group unknown to this room, and we want to bring them into the community because we identify that what they're doing would benefit the greater purpose of what we're trying to do with this.
I think that perhaps it could still be from one of these repositories, even perhaps Janusz's, because they've started to do direct bounties now on specific research problems to actually implement it in hopefully a way that will be commercially deployable as well. But yeah, it is a rapidly moving field.
Can I answer that one too? So open source is awesome, and open source is often the way that things get out there quickly. But your question was about open standards, and they're different, but they're closely related. And open standards are created under an IP framework. Kronos has one, glTF, AOUSD has one for OpenUSD. And typically those frameworks, they do ask people contributing technology into incorporation into a standard to license, but it's typically a very narrow license. So you're not losing your technology, you're not contributing your technology, you're just licensing the technology for conformant use of that technology in the context of the standard. So if you have a core technology, by all means use open source to get it out there into the community. But if you want to capture it into a standard so multiple people could use it in multiple implementations, do it under a good, reputable standards organization. You'll have a very narrow license, but you'll get that technology out there into multiple implementations, make it pervasive across the industry. So the industry has a well-worn path on how to get technology into standards without having the originators lose the rights to use it in other ways, however they want. It's still their technology, it's just being licensed. So you have that kind of sorted. So yeah.
So folks, we still have a few more minutes for Q&A. Just for the presenters, if you wouldn't mind just staying up there, it would be fast for us to move the mic. Have the projectors in your eyes, just maybe move to the side.
I can turn it off.
Were there more questions? Yeah, was there another question up front? All right, other than we have a question in the back, Neil, if you would.
Yeah.
Oh.
You got it?
Thank you, good talk. Question I have for you, it was briefly touched upon in the New York Times section about source of truth, and so thinking about biases, and we're looking at the output of this data set, so what are some of the ideas for standardization of that source of truth, whether it's the metadata, or I'm thinking even beyond in the sense of I'm mixing two or more splats together, so I have a final output, but it's actually from multiple sources. What are some of the ideas being pitched around to maybe, explain that to the viewership, or just making it clear what the level of accuracy or use case considerations are in play?
Yeah, that's a really awesome question. And we did experiment with copying together multiple splats. I think there was an example of that on one of my slides. I think combining 3D assets is something that when we've done it traditionally, there would be, our stories that are multimedia are truly that. So there would be some connecting text or joining video or something that would transition that, a lot, when we talk about sort of standardizing language or approach around something, I think that there is the technical side of that, but then there's also just like the way that we approach these things that can become a standard language. And so I just think incorporating the way that we transition in and out of them is sort of our first way that we start thinking about this. I've seen some really cool things, in my opinion, with splatting software starting to work with raw images, which I think are a really good analog for this in terms of tracing back something with any sort of like veracity to a ground truth. So for those maybe not familiar, raw images is like the raw sensor data from your camera. And so like if you're working with video, this lets you apply like LUTs with more fidelity, colors with more fidelity, but also it's showing you the raw data that's captured. So like military, law enforcement use actually default to some specific raw formats because they can trace that like forensically. So perhaps something with a completed splat file that like lets you know the source images that contributed to it, so that you could go back for that specific viewpoint and trace to original images, I think would be a huge boon to people in the visual forensics and documentary and journalism space. I think, carrying through metadata attributes from source video or photography into the metadata of the splat so that you've got creator information, camera information, copyright information, potentially location information tied directly already to the splat just by nature of the processing. I think that there's a lot that could be done there, and I think those are just a couple. Yeah.
Thank you. Great topic. Other question? I see a question up front.
I'll go back to Cesium application. So have you guys thought about the style transfer of your, imagine in Unreal, you go through the Cesium landscape and you use the generative AI to improve and lower the visual fidelity of the image to generate the splat and substitute your three-dimensional parts with the Gaussian splatting. Have you played with the style transfer or improving like with LoRa's? Because I know like a couple LoRa's already exist, but I don't know if the coherence between frames will be enough to generate the splats.
You're talking about Unreal?
Unreal with the Cesium, yeah. So kind of it doesn't matter which platform you use, you just like use the Cesium data to improve it with generative AI and convert it to the splat instead.
I haven't looked at that specifically. Our work in Unreal is just beginning as far as we're doing it.
And your implementation of splats will be just strategically placed Gaussian splatter, right? Like if somebody scanned it, so they can put it to the side. Right?
Yeah, it would be geolocated.
Okay, thank you. Thank you. Oh, just one more question about the, do you get on your web page the results of the best cameras to use, best trajectories? Because like I also wonder like if the 360 is available versus the pro cameras.
So one thing that we did not test actually was 360 cameras. We actually did, I should say, we didn't test them formally. We had one person on the team that did some 360 tests, and he did not really think the results were worth us pursuing for our workflow.
Because it's clear, right? Like just the fidelity is not there.
Yeah, I mean, there's also issues with humans captured in that environment as well, where it's just a little bit easier to use our phones or other action cameras or mirrorless cameras. Also, that's the equipment that our journalists are already working with and comfortable with. So instead of like handing people a new piece of technology and trying to train them on a process and a hardware, it's much easier for us to just, give people, tell them how to use the hardware the way that we want them to. Was there another part?
In terms of which actually was the best way I saw on the website. There are a couple of them, like 3 I would say, but it would be nice to have more examples. Let's say small scale objects, big one, like a drone production.
Yeah, I'll say really briefly that if you're looking at like commercial approaches, Scaniverse we found to be just the best thing for like building a quick model and ascertaining like, is it worth me grabbing a full rig and modeling this thing entirely? Polycam at Pro is much higher fidelity in my experience than Scaniverse, and gives you much more flexibility for outputting all those things. And then if you're working on desktop, there's some really awesome work that I know Michael is aware of with Brush, which I'm really hoping that becomes more full-featured software. But I think the best software solution on desktop right now is a powerful Windows machine running Photoshop, inputting raw images and running like 30,000 plus steps on it. We did find limits too with, images over 24 megapixel or video over 6K is kind of you're chasing diminishing returns at that point.
I can quickly add as well. For the actual input images, the sharper the individual frames, the higher the chance of successful reconstruction. Shooting with really wide angle lenses as well, like you can shoot somewhere 14 to 18 millimeters as well, is really helpful, and just avoid motion blur and try to introduce as much parallax as you can.
This is why, actually, in the post that I wrote up, and just personally, this is why I recommend action cameras, like a GoPro, or just using, if you have an iPhone, the 0.5 lens on your iPhone is an amazing tool for capturing splatting. And I think, especially if you've never done a field capture before, start with your phone, start with the wide lens on your phone, record like a high frame rate video. If you're nervous about like light and getting shaky things, like use a high frame rate video, that'll make your shutter speed faster. If you want to manually capture all the images, then pay attention to everything Michael just said. But yeah, I think start with what you're comfortable with. If anyone here like wanted to try making their first splat this week.
Look, a lot of good pragmatic advice there on the tools and how to capture the field. So we're at time, and I know we're approaching lunch. But please, if you want to come up afterwards and hang out, please do so. Let's do one more round of applause